So then our way into amines is usually via ammonia, because you know ammonia, you've been working with ammonia a long time. Can you start us off, Rich? Can you give us a property?
It's a base.
It's a base. Very good. Why is it a base?
Because it can gain H plus.
Yeah, so using that definition of base, the Bronsted-Lowry definition, yeah, it's a proton acceptor. Okay, that kind of base. Lovely.
Hydrogen bonds are present, so it's got high
Bonds. What are the conditions for hydrogen bonding to occur?
hydrogen bond to F, or fluorine, oxygen.
Exactly right. So we have to have a compound where fluorine, oxygen, or nitrogen are bonded to hydrogen. So anything with an NH bond in it, or an OH bond, will hydrogen bond. Thank you very much.
Tetrahedral and shape.
Tetrahedral. Well, it kind of is and it isn't, isn't it? If you include all the electron pairs, then they take up a tetrahedral arrangement. What if you ignore the lone pair? Then you'd say it was
Trigonal bipyramidal.
no. That would be two pyramids. That's
Trigonal pyramidal.
just trigonal pyramidal. Yeah. What's the trigonal bipyramidal? It's gone. SF6. Is that right? No, that would be octahedral, wouldn't it?
There you go. 5. Minus 3. 2.
Oh yeah. Sorry. Yes. Yeah. 5. So PCl 5. Yes. Yeah. Anyway, so sort of tetrahedral or trigonal pyramidal, depending on how many electron pairs you're counting. Ed, carry on. Because well, the lone pair doesn't count in your assessment of whether it's a polar molecule or not. What is it? Yeah, so difference in electronegativity is always what we're looking for. Yeah. Which is the more electronegative atom? So we've got an N delta minus at the top and 3 delta plus hydrogens, which of course also plays into the hydrogen bonds, because it's that the reason that only O, N and F can hydrogen bond is because they're the only atoms that cause a strongly polar bond to occur. Moving on, Harry.
Gas.
Yes, at room temperature. Okay. We've already had something about intermolecular forces. We've established that intermolecular forces are a bit stronger than others. But okay. I'll give you that. Have you got anything else?
No.
Okay, let's move it on to Ollie then.
Soluble.
Okay. It's very, very, very soluble. You can dissolve ridiculously large number of litres of ammonia gas in like 1 drop of water. So yeah, hugely soluble in water. Oh. Ben.
Can I say it's stinky?
It's
Stinky?
yes. Strong, unpleasant smell of, well, let's not go into of, Jake. It's a what? Nucleophile. Brilliant. Great. Nucleophile takes part in such reactions as substitution. So what would I start off with? If I wanted to use ammonia as a nucleophile, what would it substitute? Haloalkane, yeah. So let's say something like bromoethane. We've also seen it in another mechanism. I'm going to punch that along to Boris. Addition elimination, great. Yeah, so we saw that with something like ethanol chloride acylation. Yeah, super.
It can act as a ligand.
It's a ligand, great. Could you give me an example of a complex that has ammonia in it? We've just done this in...
AgH32.
Oh, okay. Yeah, great. Great. What is that better known as? Tollens reagent. Charge on that?
2+.
It's just 1+. Silver is a 1+ ion. Could you give me the formula for a copper complex?
CNH34 H2O2.
Brilliant. And the charge?
2+.
Great, yeah. What colour is that?
Is it with
Very good, yeah. It's that really deep blue ammonia solution you get if you add excess ammonia to, say, copper sulfate. You might start off getting a bit of precipitate because of the hydroxide, but then as you add more and more ammonia, it redissolves and you get that lovely deep blue. Did you say royal blue? Yeah. That's Tollens. Great. You've got most of mine, I think. Has anybody on the front row got anything else that we've not missed? I won't pick on you one at a time, but if has anybody got anything that we've missed? Okay, it's a pretty good list. We mentioned the lone pair of electrons, didn't we? We didn't mention that it forms coordinate or dative covalent bonds, although of course acting as a ligand is a coordinate or a dative covalent bond. But if you've got ammonia and then you add that to acid, it forms NH4+. That is of course a dative or coordinate covalent bond. We didn't get a mention of the bond angle, 107 degrees. We got the smell. Great. Okay, super. So all of that is true of amines. So I start off in this way because we've never really studied the amine functional group before. But actually it doesn't matter because you know so much about ammonia, and all of this is true for amines, right down to the ligand. You know, you've got an amine ligand, haven't you? That bidentate ligand, ethylene diamine. So if you can remember the properties and facts about ammonia, then you know enough about amines. Okay. Naming amines. Maybe about that. Who's got my blue roll? No, we need some more. The attendee. Right. if I'm going to name an amine, I've actually got a couple of options. So we could call that aminoethane. So aminoethane is like when you name a haloalkane, yeah, chloroethane, bromoethane, aminoethane. We're just saying there's an amine group on ethane, or we could call it ethyl amine. Go the other way around. We're both correct as far as AQA is concerned. Although IUPAC might prefer one or the other, they're both okay. You will often find that one is a little bit more handy than the other. So if I yeah, well, let's just use that because we've just talked about that, haven't we? If I have two amine groups, how would we name that? Say again? Ethyl diamine. You need some numbers in there. Ethyl 1,2-diamine, or we could call it Jake? 1,2-diaminoethane. So I'm trying to remember the name it's given for in complexes, but I think that's an old name that you're not supposed to use anymore. I think it was just called ethylene diamine. But that's not IUPAC, is it? That's just an old legacy name. What if I had two carbon groups on the amine? So rather than two amines on the carbon, what about two carbons on the amine? What could we call that? Go for it.
Diamino.
It's not diamine, that's diamino, isn't it? Diamino means two amines. This is
Dimethyl amine.
What have you got two of?
Diethane amine.
Diethyl, yeah? So, diethyl amine works okay. So that's obviously using the kind of the ethyl amine has become diethyl amine naming system. What if we wanted to use the other naming system? So if I wanted to call that using the aminoethane system, how would I name that? Go for it. N-ethyl aminoethane. Okay. What if I put three ethyl groups around it? Let's use this naming system first. The something amine naming system. We just call it not methyl. Triethyl amine. If we want to go for the other naming system, we'd have to call it anyone? Come on, Ben. Have a go. How many extra ethyl groups have you got? And you have to position both of them No, they're not. They're not on carbon 1, are they? The ethyl groups.
Yeah.
They're on
And then
N diethyl aminoethane. Now, so I think in this context there's a clear winner. If you have multiple carbon groups around an amine, I think it's much easier just to list them. It gets even more complicated if they're different. But if you have say if you had like a CH3 and a C2H5 and a C3H7 group all around a nitrogen, then this naming system just allows you to list them. So you can just go methyl, ethyl, propyl, amine. That's nice and easy. As opposed to whatever that would be. N-methyl, N-ethyl, aminoethane, aminopropane. I think it's easier just to list them. So sometimes there will be a clear winner. You always have the flexibility of taking two approaches, but one might be easier than the other. But they'll both be marked correct as long as you follow the appropriate IUPAC rules. Okay. I've mentioned there that we've actually got three types of amine already. So we've got our primary amine there, which is when we have an NH2 group attached to a carbon. If we have two carbons attached to our nitrogen, then it's a secondary amine. And if we have three, then it's a tertiary amine. But we can go further, because we know that our nitrogen has a lone pair, and we know that our lone pair can be donated to another group. So there's nothing to stop us from having four ethyl groups around a nitrogen. The nitrogen would then have a positive charge, so we might find that as a salt. What would that be called? Well, four ethyls is tetraethyl. And then the N plus is more similar to something like ammonium chloride than it is to an amine. So actually we name it after the ammonium chloride. So we just call it tetraethyl ammonium chloride. Okay. What's what called?
Primary, secondary, tertiary.
Oh, yeah, thank you. What comes next? Biologists should know the answer. You do it all the time with proteins. Quaternary. So it's a quaternary ammonium salt. Can I have another red? No. Quaternary ammonium salt. Right. Let's. We mentioned. We mentioned that our amines act as ammonia and amines act as good nucleophiles. So there's one of the red. Let's just recap the mechanism for nucleophilic substitution. Of bromoethane. I'll leave a question mark there. I'll get you to fill that in a moment. Could you write me a mechanism for that reaction? Thanks. Can we come back? Start us off, please. Someone. Start us off, please.
So I just say,
Hey?
so I just tell you it.
Yeah, sort of describe it, you know, create a...
So an arrow goes from the lone pair on the NH3 carbon.
Arrow goes from the lone pair on the NH3 to the...
Carbon.
Because...
Carbon is delta positive.
Because carbon is delta positive. Great, thank you. Because of the more electronegative bromine, just put CH3 there. A bit more, please.
Oh, and then an arrow goes from the bond between the carbon and bromine to the bromine.
Yeah, from the carbon bromine bond on to there. So we've got CH3C. We've now got NH3 on there. And the Br minus has gone somewhere else. Come back to that in a moment.
And a plus on the nitrogen.
There should be a plus on the nitrogen. Thank you.
And then I didn't know if it was with excess NH3 or not. But
That's a really good question, and I will come back to that in a minute. It's a pretty crucial question, actually.
yeah.
Let's assume it is for the moment.
So another NH3 would its lone pair would go to one of the hydrogens on that nitrogen.
Yeah, so the crucial bit is that one of the hydrogens leaves and the arrow goes from,
The hydrogen nitrogen bond to nitrogen.
yeah, from the bond to the nitrogen. We often see that going in the wrong direction. If you want, you can also add another ammonia there, taking that hydrogen away, but it's not a marking point. So I don't usually put it on the board, but you'll see it in textbooks. Okay, super. And then we've got so what's the other product? How do I balance? Let's go to somebody else for that. How do I balance this equation? If you're asked to write a balanced symbol equation for this reaction, what do we need? What do you think, Ollie? So therefore, balanced symbol equation? It's not balanced. We need a 2 there. Okay, so that's the bit people often forget. If you want a balanced symbol equation, we need 2 ammonias, and then we can have ammonium bromide as our other product. Yes?
Why doesn't it make HBr?
Because ammonia is a base. So if there was any HBr made, which is an acid, it would just react with the ammonia to make NH4Br. There's other reasons to have an excess ammonia, which I will come back to maybe today. Okay, I'm going to come back to that reaction in, I think that might be another show. Another episode. Yeah.
So you need an intro.
Sure. Yeah, I'm just gonna do that.
Do you want us to make you an intro? Make an intro.
The one of the reasons I resist, extra production on top of the videos is I want to be able to take my phone off there and plug it into the computer and stick the video on, and it's done. I don't want to have to do stuff because it just there's like well over 100 videos on there now. I haven't got time to produce every video.
I'll be your editor.
Fantastic. Yes, that would be fine. But I'm not doing it myself. Okay, making. NH4X. Okay, so one way of making amines is where we have a haloalkane, we react with excess aqueous ammonia, and that will give us, I'll write that on actually now. There we are. We're talking about bands from the 80s. No, we won't. We're talking about movies from the 80s, weren't we? Thelma and Louise. Anyway, in excess. Well, you can look them up. The other ways we can make amines is where we have the hydrogenation of a nitrile. A nitrile, remember, is a CN group made from cyanide, and we hydrogenate those with hydrogen in the presence of a nickel catalyst. It says high temperature there. I thought it was about 60 degrees. Okay, it must be a different one. High temperature and pressure. It's an important reaction because a CN allows us to put another carbon on the chain. So if I had, say, bromoethane, and I wanted to make that carbon chain a bit longer, I could start by reacting with the potassium cyanide to make propane nitrile, and then I could take my propane nitrile and react that with hydrogen to make yeah, let's just do that. No, yeah, yes. To make my propylamine or aminopropane. So it adds one carbon to the chain. Oh yeah, and I can also do that with, sorry, there's another one there. No, let's go for an A. I can also do that with a hydride. Do you remember hydrides?
Oh yeah.
Or I can hydrogenate NO2 groups with a tin catalyst in HCl, what used to be called nascent hydrogen. That means that where the metal and the acid is making the hydrogen in real time, and then the hydrogen's reacting, rather than getting hydrogen from a big cylinder of hydrogen and passing it down a pipe. I just want to talk about balancing those, but I'll give you time to scribble that down. Long time ago, before your version of the A-level came out, there used to be separate papers in the A-level, and then there was an organic paper, and then there was a physical and inorganic paper. But They were completely separate parts of the syllabus. And what that meant was that they didn't ask redox questions about organic reactions because the inorganic and the organic were separate parts of the syllabus. So when it came to balancing oxidation reduction equations in organic chemistry, they didn't want to use electrons and stuff like that. So they came up with a workaround, which I've only ever seen in AQA. And that's where we look at the total amount of hydrogen that's been added. So if I want to balance this equation, I've got NO2 there, and I've got NH2 there, but of course the O's have got to go somewhere. Where are the O's going to go? In redox chemistry, by balancing O with H2O. So 2 O's would mean I'd have to have 2 waters over there, and then I just count up the number of physical hydrogens that I've got. 1, 2, and 4 makes 6, and I put a 6 H in square brackets there. And then that counts as a balanced equation for the reduction of a nitro group. I could do something similar here. So I could say if I added 4 H's there, then that would make the amine there. So like I say, it's just a workaround, but it still has to balance. I still have to have the right number of H's on the left. Okay, I think that's quite a good place to stop, partly because we've almost run out of time, but also because the last 2 topics are interconnected. Yeah.